Good morning, everyone. So this is the second class. In a way, we started the nonlinear classifiers in the previous class. What is the example that we have taken to illustrate the necessity of nonlinear XR problem we have taken, right? So where you have here X1 and these are the two feature components of your feature vectors that you have considered, assuming that this belongs to, let's say, class A, there is an element belonging to class B, another element belonging to class B, and here class A. Okay. So here it is 1, 1. If you take it, this is one class, and these two belong to another class. So then you would realize that there is no single linear line that you could draw here to separate them. As I was mentioning in the previous class, this is a trivialized example to see or to illustrate, for that matter, how where you would require, for example, a nonlinear classification. See, if you want, we can take it this way also. I could even have negative feature vectors. Even if I don't take that, assume that I have some samples here. Samples means in my training vectors x bar, if I plot x1 and x2 for one class, I am getting here, and for the same class I am getting some samples here. Okay, and there could be other samples which are coming there, and so each one showing you one thing. So this could be one scenario. So this is just to make it clear to you, it is not just XR that we are talking about. It's a trivialized example to see the phenomena, but in practice you could get it this way. Then what will you do? Similar to the earlier one, you might find a line here, you will find another line here, correct? Two lines. It could go on and on. It need not be always two lines. Consider I have again here, for some reason, I have class here. This class is repeating here. Okay, then I might draw some other line here. So this can go on and on. So which also tells you now, not always two neurons in the hidden layer may be good enough. You might require more as well. Okay. Anyways, so this is a kind of an expanded version of XR problem that we have seen. How are we solving? Like one of you were asking why 0, 1 and 1, 0, only one of them is coming. So that you could see it from the example itself, because you are taking the outputs are the outputs of and R equivalent classifications. So there you would realize there is only one combination, depending on whether you are considering R first or and first, it will be either 0, 1 or 1, 0. Okay. So even last time, if you consider R, if you just flip them, instead of 0, 1, you would be getting 1, 0 also. That is also possible. So you could see that even from here, if you want. How can you see that? Let's call this as G1 of X bar. So the case is now you have a hidden layer where you are taking how many neurons now? In the hidden layer, how many neurons are there? 2 neurons are there. So one neuron, you are magically finding out this line. We'll come later on how to find this line. But for now, you just tell where we want the line and the line appears. Okay, we need to later figure out how that line, we can arrive at that line. Right. So there is another line here. This is G2 of X bar. Assume that this is negative. Right. The linear classifier, what does it do? On one side, it is negative, and another side, it is positive. So this side, it is negative. This side, it is positive. Similarly, here for G2, this is negative, and this is positive. Again, we are assuming that it could be the other way around. Convention just gets flipped there. Right. If you recollect, there is a summation going on, W1 X1 plus W2 X2 plus WX0. And after that, we are doing a logistic simplification of that. What is it that we are doing there after doing the summation? Do you remember the neuron diagram we have drawn in the last class? What will you do? activation function, right? That will give you either 0 and 1, because any negative value is essentially one class, any positive value is essentially another class. It is good enough to say that this is 0 and that is 1, isn't it? That's how you are using a step function there. After your summation, we have separated in one diagram, and while we are doing it, we combined also later. So look at this. If I do it, what will I get on this side? Can you tell me now? I will get 0. This is negative 0. This is also negative. So I will get to this whole region 0, 0. And what about this region? Again, G1 of X I am considering as the first element for me. This is positive. Okay. And this is negative. So I will get 1, 0. Then what? Here, this is positive and the other one is also positive. So I will essentially get 0, 0, 1, 0, 1, 1. And of course, make a note here, if I had written this as G1 of X bar and this as G2 of X bar, I could have slightly got it a different way. This would have been 0, 1. Clear so far? So this is the reason why you are getting only 3 possible things there. This could vary on the type of distribution you have, right? I could very well get 0 and 1 also. Maybe not if I have drawn it this way, but a different way of lines, I may find out that as well. It is possible, right? Some of them are not possible, but some other combinations will be definitely. Another important point that has been mentioned in the previous class is when you are using a simple step function as your activation, the whole region there is getting mapped to what? This has been mentioned in the end of the last class. This whole region is getting mapped to the vertices of a hyperplane, you can call it hyperplane. Can you say the length of your hyperplanes also across each axis? You can tell 1, that's all. See here, in every one there is either 0 or 1. So this is a very, very important point. You are finally, a whole region is getting mapped to just the vertices of a, some places they are calling, if you start from 3-dimensional x1, x2, x3, that is a cube is what you are getting. They call it as a hypercube. Anything above that you cannot say, so you call it as a hypercube. Or a more generic word will be to call it as hyperplane. So a hyperplane whose, and on that hyperplane, that's a unit hyperplane you can call, because the lines or the lengths in each direction of this x1, x2, x3, x4 is at max is 1 only, and you will get only either 0 or 1. Only at those points you will be getting that, right? So what happened here now? After this transformation, if you look at it here, let the output of these two things, let us call one of them as y1 and another as y2, right? You got 0, 0, and then you got 1, 0. Okay, now this is where I last time drawn it, but now given that this is 1, 0, I'll get it here, and there is 1, 1. 1, 1 means here. So you see here a square here of length 1, and also note that there is one which is kind of 0. One of them, which one am I calling as class A? So this is I am calling as class A, which is 0, 0. So this is A, and then what else is A for me? This is also A, 1, 1. This is A, and this is B for me. Correct? All I need to know is what should I do now? Again, y1 and y2 should go to another neuron. You figure out again a line that separates them. That's what the neuron does, and that a line something like this would be, that is not good enough because it is not separating. I should get a line like this, correct? Because then A and B are getting separated. So essentially, if you want me to draw the diagram, I think I will not do it because last class also have done. You have two neurons from x1, x2. You could have L features are 2 here. From each one to each neuron, inputs come. There is a bias function that you give to each of them. you have y1 and y2. Again, these two will go to the second one, and this one you call it as a hidden layer, and this, the final one, you call it as a output layer. The outputs of these hidden neurons are y1 and y2. Any chance of getting here, what is the value here? This is nothing but 0, 1, correct? This is 0, 1. Where will that be here? So it means, what does that mean? G1 of x should be negative, correct? And G2 of x should be positive. Is that possible? That combination itself is not possible, correct? So this is, they call this word polyhydra. So polyhydral regions, they are calling it that. I'm not used to that word earlier, but there is something called as a polyhydral region. So each region you are getting in the higher dimensional space, that they are calling it as each of them is a polyhydral region, they call it. So this is never possible, if you notice. For at least this specific scenario, that is not possible. So this represents, this is still a unit square here, but this they refer to as virtual polyhydral vertex, a vertex representing a virtual polyhydral region. Okay, that is just for the terminology, but telling it in common terms, this is a vertex that represents a region that doesn't exist. That's all, as simple as that. Because you never get that. If this is negative, obviously the lines are such that this has to be also negative. It cannot go to the other way around, unless I draw a line something like this, then it is possible. Then it is no more a virtual node, or a node that represents vertex, that represents a region that doesn't exist. Okay, so as I mentioned, this need not restrict, this need not be restricted to just two neurons in the hidden layer. You can have multiple neurons also. What would be the impact of that? Let's say so this could be my G1 of x bar, G2 of x bar, G3 of x bar. Maybe my whole points are in this region. Let me extend this also just to cover the whole region. Then how many sub-regions it has done? 1, 2, 3, 4, 5, 6. 6 regions have come. And again, you consider that this is negative with this side, positive this side, negative this side, positive this side, negative this side, positive this side. Can you now tell me what would be the outputs of, for this region, will be represented by which vertex? Can you tell me that? So for the G1 of x, it is 1, right? So easy thing is, let us keep the first one first. Okay, G1 of x, wherever it is positive, this is positive. Anything above is positive. So this is positive, this is positive, this is negative, below this, negative, negative. G2 of x, this side it is negative. So this is 0, 0. The rest is 1, 1, 1, 1. G3, where is my G? Yeah, this is G3. This is all negative. So this is 0, 0, 0. This is also 0. And this is 1. No. We assume that all means, of course, what you are saying is this way. Yeah, just let us assume that is possible. Yeah, you are right. Just that, assume that this is my region where I have points, and doing that. This is true. This can go on here as well. For this, the way I have drawn it, it is possible. They intersect, right? Yeah, so this below this also, again, it can give you different regions, right? Okay, assume that that's why I have drawn some boundary telling you that this is where I am looking for, and my samples are distributed within this. There is a very interesting theorem that tells you that if I assume that I have still two classes, but I have a feature vector of size 3. And suppose if I am able to separate these classes within these regions, means the class, no two classes are messed up together in any, or mixed up together in any of these regions, they are separated. If that is the case, and assume that a class A is in K regions, then if I use another hidden layer with K neurons, I am guaranteed to arrive at a solution. I am first making the statement now, just pay your attention here, then we will decipher that and see why that is the case. What I am saying is, see, this was the original case. I have taken two lines. Then what happened? In each region, this is the, I could have drawn this polyhydral regions also. This is one region, this is one region, this is one region. What happened now? I am able to separate class-wise these samples into one of those regions. In other words, no region has samples from both the classes. So what the theorem says is, if I can manage to do that, so this way two were possible. As I said, if there are something else, you will take one more thing. And as long as your first hidden layer, whichever you are doing, if you are able to separate the classes, each class is there in one of the regions, but no two classes are there in the same region. If that is the case, assume that class A has K. Class A is present in K of those regions. And if I use K number of neurons in the next hidden layer, there is no hard and fast rule that I should use only one hidden layer. Now I am introducing one more hidden layer here. If I do that, I am guaranteed to perform a classification of these two classes without any problem. At least is the statement clear? Then we will see why. The proof we will see, we will construct it by logic step by step, we will do that. But first of all, is what the theorem saying clear to you? As long as my class A is here, this is my class A samples are here, class A samples are here, okay? The rest of the samples are B. If that is the case, use one more layer which has 3 neurons, and then you will be able to separate class A from class B. Now you are not able to separate them. Of course, you may be able to separate it even with less number of neurons in some cases, but this is telling you it is guaranteed to separate, irrespective of how they are distributed. Okay, is the statement clear, or do you have any doubts or queries about the statement? The theorem part, the proof of that and why is it so, we will come now. But before that, I just want to ensure that you understood what the theorem says. So maybe I will just draw you the diagram also there. What it is saying is, let's say I have used 3, how many hidden layers I have you in the first hidden layer, how many neurons are there? There are 3 neurons. That's why I got G1, G2, G3, correct? So, well, so inputs could have been any number. I have not put any restriction there because all that matters is how many outputs are there. So I could have any number of inputs here. So let me call that as X0, X1 to L dimensional 1. XL I have. Okay. When I have this, now this everything goes to everything here. And this, each of them has this. And then of course, for now you consider step function also inside. There is a step thing also is there. Now, assume just to avoid one more region also, let me for example consider 6 regions are there. Huh? Okay, let me consider only 2 regions here. Okay. Well, as I said, there could be instances where you could do it with less number also. This is something that guarantees you. So assume that my region class A is spread in just 2 polyhydral regions there. If that is the case, now if I use 2 neurons here, and then what will happen again? My inputs will go here. And of course, this bias term. And of course, finally, I'll do a single neuron is my last layer. Output layer is a single neuron. Then this is my output Y. This is guaranteed now that this will separate the two classes, provided your algorithm you are doing it in the right way. This guarantees you that you will arrive at a solution. And of course, this is a hidden layer. This is a hidden layer. This is your output layer. This hidden layer 1, hidden layer 2, output layer. Any output layer means that's the final output. There is no 1, 2 there. This is your inputs. So you are using 2 hidden layers here. Okay. Say, for example, anyway, I have drawn this, taken time to draw this. So let me also draw here the how do they get mapped at the end of this thing. How do we know that? We already have seen that. Say, I could, for example, consider x1, x2. There are 3 here. x3. Okay. So again, I'm doing a slight abuse of notation. I was earlier using x1, x2, x3 here, but you name it whatever you want. Okay. That's the kind of thing you have it. So now if you look at where they get mapped to, okay. So consider this as my origin. Now, where does that 0, 0 will go? This is my origin stuff. Okay, this is my direction. So 0, 0, 0 is here. And then what? 0, 1, 0. So here 0 along x2 1, right? And then 0, it doesn't move along this direction. So this is my 0, 1, 0 and 0, 1, 1. So from here I will also go here. This is 0, 1, 1 and 1, 0, 0. I move along here 1. I don't move along any of those directions. So this is my 1, 0, 0, 1, 1, 0. I move as 1 here, and don't move anywhere. Just stop there. This is 1, 1, 0 and what? 1, 1, 1. Okay. So it has to be the extreme. 1, 1, 1. As you could notice, the rest of the vertices represent regions that do not exist or maybe outside your area of interest also. Now, see here. Depending on where your classes are distributed there, you may sometimes find a plane that separates 2, and sometimes it may not be possible. If you are just going for a single output layer here, so this is the output at this end of hidden layer, you have this output. Now, if I right away go to this one, it may so happen. How do you separate now? The next one should give you a line in 2D. This is a 3D. You have a plane. You should come up with a plane. For example, this plane could be, again, it's too much to ask from me to draw all these planes, which I'm pretty bad at, but I'll try to do something. So assume that this is the plane, and assume that 0, 1, 0, 0 and 1, 0, 0 belong to one class. This you could separate. But suppose there could be a combination among these vertices where a single plane is not good enough. But what the theorem now is saying is, when will this converge? To what extent should I go? If that is the question, what this theorem is saying is, are you able to separate class-wise into one of those regions? If you have done it, don't worry. All you need to do is take one more layer, hidden layer, and let the number of nodes could be minimum of, in fact, class A and class B, because one of them you have to do, and put those many layers, neurons there, and your job will be done. There is a catch here that is telling you they should be separable here in terms of the regions. Okay. So if 3 are not enough, go for 4, Are you able to do that? 4 are not enough, 5 you go. Can you do that? If you do it and tell me now, among how many regions your class has spread, I will tell you. The next layer you have minimum of number of spread for A and B, and with that layers you should be able to do that. Okay. So how is that possible now? Let's make a look into that. Let's take a look into that. See, assume that my class A is spread at k nodes. My class A is spread at k nodes. So the k could be, for example, this node, you take some combination. It is spread at k nodes. Now, can I not come up with planes that separate each of these? Let me come up with k planes, each of them separating one of these nodes from the rest. Can I do that? I can always come. See, if you want me to separate set of nodes, I have a problem. If they are nicely aligned, I can do that. If they are opposing each other, I can do little there. But node wise, I can separate each student wise, I can do. But if I want to make you into group wise, that is where I have a problem. Sometimes you may converge and sometimes you may not converge. So the point here is, I use now k planes, each of them separating one of these k nodes from the rest. Clear so far? So those are the ones representing here. Okay, and now you find that hyperplane is given. See, the moment I want a hyperplane, I want a neuron. If there is a neuron, that gives me one hyperplane. That's why I am telling now there are k neurons here. Follow carefully here. Now, if a sample from class A comes, that is how now I constructed. Okay, my k equal to, say, 2 is a very trivial example. Any 2 you could separate. So that's a means after doing such a big gymnastics here, let me keep one more thing also, otherwise it is looking too trivial there. Okay, so let me further entertain you with my unlimited drawings here. Just one more I have kept. Okay, don't ask me to draw more, please stop here. So I have taken 3 now. 3 I have to find out thing. Now what had happened, these 3 hyperplanes are, again I said that right now you possess a magic wand. You just have to tell what do I want. You tell that I want a plane that separates one of these k into the other. You got it. Okay, how you get it, you still have no clue. But for now you assume that. Now what will be the outputs of these things? Suppose when a sample from class A comes, can you tell me about the comment about the outputs? Very good. One of these outputs will be 1, the rest will be 0. It could be 1 0 0, 0 1 0, 0 0 1. There is no other possibility here. If it is from class B, any region it is coming from, the sample is coming from class B, what will be the outputs? Huh? All are zeros, because that is not there in any of these hyperplanes. So your output is guaranteed to be 0 0 0 there. What this fellow has to do here to get the correct output? What operation he has to do here on these bits now to get the output of 0 1 here? For one class 0 and another class 1, what this guy should do? Simple OR, nothing else. You see, either if one of them is 1, you make it 1. If all are 0 0, you put any number of conditions, he will never pass, he will fail. Okay, wonderful candidate, he will remain there itself. That's the class B. So do you see logically now that if you are able to, in this first layer, hidden layer, if you are able to bring it to separate them into one of those regions, still there is not linear. A linear line is not doing the job for you, but somehow you managed to distribute them, subgroups you made. Okay, divide and conquer. You first divide the whole class. There with a single statement I am not able to do, make some small groups, but at least those small groups are consistent. And then I will do R. I will come up with some other. So is it clear to you that if it belongs to class A, I should be getting one of these outputs? Okay, see, my hyperplane is such that it has a vertex, it separates that vertex which has class A from the rest. Okay, I have 3 such vertices, I have 3 such hyperplane. You are guaranteed that when it is class A, it will be either 1, 0, 0, 0, 1, 0 or 0, 0, 1. There is no other possibility. When it is class B, it has to be 0, 0, 0. Because in any of those, again, positive, outside positive, this side negative. So this has to be 0, 0, 0. From any other vertex other than those k vertices. You have only k vertices here. Yes. It will work, but again you need to extend it. This is not a simple OR gate then. This is something else. I cannot manage probably here with one OR gate. I should do something else here. It will not right away work. Need to extend this logic there. That's a very good point. Correct. Where? No, see, if it is 3 ones, what is happening? This way we have hyperplanes that separate only these things, that will be always 0 here. The output will be 0 for that. See, look at my hyperplanes I have drawn. Now what I have done? I have drawn again some hyperplane here. Okay, 3D. I draw with. I show it this rather than make any mess there. This is one hyperplane. Okay, assume that another one is these 2 are there. This is one hyperplane. This is one hyperplane. So anything outside is 0. So that's why any of the other things I would always get 0, 0, 0. Again, the catch is in practice, this having this background on what happens when I am increasing number of neurons there in a given hidden layer. What is happening if I am putting more layers there? This some intuition should be there. So that's where probably this will help you to get some idea. And also there could be scenarios where once you do it, you can visualize things, of course, provided your x1, x2, x3, somehow you manage them to bring them to lower dimensional space. If your algorithm has 100 feature vector of L equal to 100, it's not so trivial that you could directly see them. Other than for those we give the assignments to you where we just restrict ourselves to 2 or 3 feature vectors. Okay, beyond that, you need to somehow find out a way, figure out a way to do that. So just to tell you, this forms hyperplanes. So let me, this forms hyperplanes, and this forms the regions. That's how it is told there. Essentially, then it's the regions you are getting here, which region it is there and all you are getting. So typically the first is forming the hyperplanes, those hyperplanes there, and then it is giving you the vertices, and in the next layer, this is giving you some regions there. That's what you can tell there. I don't want to start back propagation now, but I will give you some kind of motivation for back propagation and will prepare you for back propagation. So as a part of it, let us first have a relook at the activation function. Earlier, we considered, so by the way, we can all philosophically talking, things will be wonderful even about back propagation. So that's what we will do now. Well, as we discussed, how do you find all these lines and everything? So far we had magic wand, now that got vanished. It is no more there. Now you have to find out a way to do that. How do you do that? What should be the way? We have done it earlier in some small scale earlier, we did it. You could use that in the linear classifier. You could use a similar technique here. What will you do there? You know, you have a training samples you have with it. You know what to expect from it. You build it. You just throw something here. You stand here and see what you are getting and compare it with your code book on what you should get and see the error, sum them up. Okay. If it is very bad, convey this information till here. That is where the technique is. Each layer, each neuron, it has to come. Everybody has to be in straight line there by the time it comes here. It has to propagate through all the neurons. That is where the trick is. How did we do it with a single neuron? how are we making the corrections? What is helping us? Gradient. Very good. You are finding out the gradient descent, right? That gradient descent is helping you. So here also you cannot avoid gradients. There itself we had a gradient, one neuron, very well behaved, a single student dealing with a single student. Now we have a mass of students. They themselves are out of control, so we cannot do much. Same is the case here. You do not know which neuron, which hyperplane you have, but everything you need to align just by standing here and seeing there and passing back the instructions. That is what the back propagation you need to do. And in that, similar to the way you did it with a single neuron, here also you have to compute gradients. And we have a very ill-behaved person here at every neuron. What is that? Particularly when you are computing these gradients. The step function itself is ill-behaved. You cannot find out its gradient. So we will get rid of, we will smoothen the step function. Okay, don't be so hard. We will make it that smoothened out. How do you do that? So earlier you have this function. We smooth it out. We don't want these, okay, these pinching corners. We want to smooth it out. Or it depends on to what extent you want to smooth that out. So first thing you do is you make, he is the radical guy, you tone him down. Okay. Earlier your, let us call that function f of x. Earlier it is 0, 1, okay, x less than 0, x greater than 0. Can you suggest something? Any idea of what would be the analytical expressions for these guys? Excellent. I think you have it from the DL course. F of x equal to 1 over 1 plus exponential of minus a. Minus a, x is completely missing. This is nothing to do with x. So let me put somewhere x also here. Exponential of minus ax. What is going to happen here? As I go towards high value of x, this will die down completely. Exponential of minus x will die down, becomes 0. I have 1 there, correct? What happens on the other side of negative x? This is becoming so high, this becomes a monster, that this whole thing 1 by infinity or very large value becomes 0 here. And the rate at which this happens, the exponential decay or increase depending on whether it is x is positive or negative, is controlled by this a parameter. You take a control of a. If it has to done very steeply, what should be the a? Otherwise, the rate of exponential you are controlling with a. Okay, this is one thing. This is the, we will now change from the ideal world to the real world, where the first casualty of that is no more step function. This is, what is this referred to as? Sigmoid function. This again is a, again there will be instances, if you remember, this is not the only way you could do. You could have taken this f of x to be 1 and minus 1 also, where 1 is greater than 0, minus 1 is less than 0. Okay, can you tell me what would be the equivalent smooth and ironed out version of the activation function? So what you have now is, this is minus 1, this is 1, okay, this is 0 here for my x. Well, earlier jump was 1, scale it to 2, first stretch him in the vertical direction. How do you do that? You want to stretch this in vertical direction, what will you do? 2, just scale it by 2. I have 2 by 1 plus exponential of minus ax. Now, what is his territory now after I scaled him now? He is from 0 to 2. Okay, enough stretching, drag him down by what? Minus 1. So that it is from minus 1 to plus 1. So this is also, there could be instances where you might consider minus 1 to 1 or something else, but essentially you would realize that this is kind of good thing. And then there is also a family of curves that comes from hyperbolic tan function, which also a special case of that could be these things. We will not go into those details. This is good enough for our purpose. Again, as I said, the devil is in the derivative here. So somewhere you have to find out the derivative of this function also. Let us finish that formality now. And even before that, let me tell you one more casualty as a result of changing this. Can you tell me that in terms of what I have drawn there, what is the second layer doing, third layer doing? Can you tell me what is the consequence of moving from step function to this? You are no more restricted to mapping to vertices. You are now spread there. That is also happening. So then that is why now perhaps me writing there somewhere, I don't know whether I erased it. Yeah, forms regions. So now when you have it, it is not just a vertex, but you are separating their region, because it doesn't simply get, see what mapping 1 is only if you take 0 and 1, it can go and comfortably sit at the vertex. But now we are allocating, we have put chairs in between also. There is no space left to move from one chair to other. It can sit in any of those chairs in between 0. Okay, so that is another casualty or consequence of that you need to keep in mind. Right. So to come back here, what essentially you will do in back propagation algorithm, as long as you have a coffee table discussions about back propagation, that's very simple. You compute the error here, okay, and then you take the derivatives of that and propagate the error here. Again, then you keep on propagating here through derivatives, and you again, once you do it, at the end, see what's the value. Look at the overall error, okay, and then if it is accordingly, now you repeat this whole process until it converges, and exact derivatives and everything we'll see in the next class. Okay, maybe we can take 2-3 more minutes. Let us also finish what is f dash x here. Can you calculate and tell me? Okay, this also I will drop for now because this is good enough for us, huh? For most of our things. This is just to let you know another possibility. So this I will drop. So just consider f of x equal to 1 by 1 plus exponential of minus ax. What is f dash x? We'll do this and finish it off there. What is f dash x? Okay, n into x power n minus 1 is all that I remember in derivatives first thing. So I write it as 1 by exponential of minus ax whole to the power of minus 1. So I have minus 1 into 1 plus exponential of minus ax. What next? Chain rule. You take the derivative for this. I forgot already. Minus 2 there. Okay. And what is the derivative for this? Multiplied with 1 is 0, exponential of minus ax, minus a into exponential of minus ax, minus minus plus. Okay, so I could write it as a times 1 over 1 plus exponential of minus ax into exponential of minus ax over 1 plus exponential of minus a. See, finally, I want to express this also in terms of f of x. That's why I'm doing a small drama here, where I am separating these two different terms here. Okay, so this would be equal to a times f of x times, what is this? 1 minus f of x. Okay, that's the derivative we'll be using. We won't derive it again and again, so just keep this in mind. Okay, now we will stop it here, and